Nuclear energy 2. This is my second nuclear energy video, and this is about nuclear fission. It's a very special type of decay, nuclear fission, and it's one of the big fat boys. A very large nucleus will be unstable because it's too big, and it will split in two. If it's a fissile isotope, it will split in two. Basically, nuclei can't be too big. Like, imagine water drops. You can't get very, very, very big water drops. They will tend to split in two. And this is why there are no stable isotopes with an atomic number greater than 84, because they'd be too big to be stable. Note that when it does split in two, we also get 2 or 3 neutrons. And in an earlier video, the graph of n against z and the ratio of neutrons to protons explains that. And then if we work out the binding energy, what we start with, what we end up with in terms of mass, then we can work out the energy released. Looking at this graph, basically what's happening is that a big nucleus, for example uranium-235, is splitting into 2 smaller fragments, and those fragments will be way to the left on this graph. So the average binding energy per nucleon is greater, therefore the particles are deeper in a well, therefore energy has been released. And in most nuclear power stations, it is an isotope, the isotope uranium-235. An isotope of uranium is used as the nuclear fuel. A few things about uranium-235. Where do we get it from? Well, it's dug out of the ground. Uranium ore is mined, and uranium ore typically contains about 0.7% of uranium-235. The uranium is extracted using a chemical process, and then there's lots of different isotopes. So to get the U-235, they use centrifuges, hundreds of centrifuges apparently, and then the uranium-235 is made into pellets that go into fuel rods, and then the fuel rods go into the reactor. Now, uranium-235 has a half-life of about 700 million years. So basically, if we leave it alone and do nothing to it, then not a great deal is going to happen. We need to encourage it to split. How do we encourage it to split? Well, basically, we get it to absorb a neutron. And if it absorbs a neutron, then it's much more likely to split, to undergo a fission event. And where do these neutrons come from? And if you remember your GCSE, you'll remember this idea of a chain reaction. If at least one neutron from a fission event goes on to cause another fission event, then we will get a chain reaction. And if we can control this reaction, then we've got nuclear power. If you can't control it, then you've got a nuclear bomb. Here's a typical fission reaction. Uranium-235 absorbs a neutron, and in this particular case we get an isotope of barium, an isotope of krypton, and 3 neutrons. Notice 3 neutrons are released, which could potentially cause other events. This particular reaction releases about 200 megaelectron volts of energy, which is mostly the kinetic energy of the fragments. It's like a little explosion. Notice that the nucleus splits asymmetrically. One of the bits is bigger than the other one, and the fission fragments are highly radioactive. They are nasty, which is why nuclear waste isn't very nice. Now, the neutrons emitted are very fast, and the chance of a fast neutron being absorbed by another uranium nucleus is very small. Because it's traveling so fast, it spends very little time in the vicinity of the nucleus, and the chance of it being absorbed is very small. So we need to slow them down, and we slow them down using something called a moderator. And a moderator is a substance which doesn't absorb neutrons, and when the neutrons bang into it, then the neutrons lose kinetic energy, and so we go from fast neutrons to slow neutrons, which is what we want. Good moderators include graphite and heavy water, which is D2O. Control rods are substances that do absorb neutrons. They gobble up neutrons. Boron is a very good substance for this. And basically, if we raise and lower the control rods, then we can control the rate of reaction by controlling the neutron flux in the reactor. If we lower the control rods, then there are less neutrons buzzing around and the reaction slows down. The other important part is the coolant, which takes heat energy away from the reactor. For example, liquid sodium, pressurized water in a PWR, or carbon dioxide in an AGR, an advanced gas-cooled reactor. And that takes heat energy away from the reactor, which we can use to make steam, to drive turbines, etc., etc. So what's good about nuclear power? Well, it doesn't contribute to global warming, which is a big issue at the moment compared to fossil fuels. It doesn't cause air pollution, doesn't cause acid rain, and it's very reliable. It runs 24 hours a day, producing lots of electricity. What are the problems with nuclear power? It is not renewable. There is a limited supply of uranium-235, which is currently dwindling. People are looking for other fissile isotopes like thorium, which they could use. The biggest problem is dealing with nuclear waste. It's very, very expensive to deal with. Some of this nuclear waste is going to be dangerous for thousands of years, for longer than the pyramids have been on Earth. We're going to have to look after this very, very nasty nuclear waste. Very expensive, and all kinds of security issues as well. Decommissioning costs. If you have an old power station which needs knocking down, it will literally cost billions to knock it down. You can't just go in there with a bulldozer, because every single brick of the power station is nuclear waste. If an accident occurs, it could cause major, major problems. Do accidents occur? And every now and then, yes, they do. And the other thing about nuclear power, are there safer, cleaner and cheaper ways of generating electricity? And the answer is actually yes. We don't need nuclear power. There are countries now which get all of their electricity from renewables. We don't need nuclear power.